Good day, everyone. My name is Darren Limibao, and today I will be discussing about Chapter 19, Thermal Properties. So, let's start. Thermal property refers to the response of a material to the application of heat. As the solid absorbs energy in form of heat, its temperature rises and its dimensions increase. The energy may be transported to cooler regions of the specimen if temperature gradients exist, and ultimately the specimen may melt. Heat capacity, thermal expansion, and thermal conductivity are properties that are often critical in the practical use of solids. And after studying this chapter, we should be able to define heat capacity, identify how solid absorbs thermal energy, calculate the linear thermal expansion coefficient, explain thermal expansion, and the definition of thermal conductivity. So the first topic that we will be talking about is the heat capacity. Heat capacity indicates a material's ability to absorb heat from the external surroundings. It represents the amount of energy required to produce a unit temperature rise. Typically, heat capacity is specified per mold material, and its units are either joules per mole Kelvin or calories per mole Kelvin. And heat capacity can be expressed as follows. It is C over dQ over dt, where dQ is the energy required to produce temperature change, and dt is the temperature change. So, next up, we got vibrational heat capacity. Internal energy increases because atoms vibrate more vigorously. And it is also described by a lattice vibration. Phonon modal. At very low temperatures, atoms vibrate very, very, very little, as opposed to higher temperatures where they vibrate more, and the heat capacity is small. And at high temps, vibrations approach constant amplitude, and heat capacity approaches approximately 3R for many solids. And here we got the temperature dependence. As you can see here in the graph, it is a graph of temperature dependence of the heat capacity at constant volume, and the theta D is the Debye temperature. At temperature equals 0, CV is approximately 0 as well. And the rapid increase until reaching approximately theta D. Oh, sorry about this part here, but this shouldn't be here, so let's just cross that. I forgot to remove it. So, on to the next. Temperature dependence at low temperatures. At low temperature, heat capacity varies as CV is equals to ATQ, where A is the temperature independent constant. This relationship holds until reaching the Debye temperature, theta D, where the heat capacity becomes nearly independent of temperature. Typically, the theta D values for many metals are usually less than room temp. And for many ceramics, it's really high, like hundreds of K. So we're good with that. Next up, we have thermal properties for variety of metals. So as you can see here, it's like a big table. There's like a lot of going on. This table shows each material's heat capacity, coefficient of thermal expansion, and thermal conductivity. When we compare metals, when we compare materials, not metals. So we could start with metals here. Metals generally have high thermal conductivity, meaning they transfer heat very, very easily. Copper and aluminum are really great examples. For ceramics and polymers, typically have much lower conductivities and much lower expansion rates. And steels fall somewhere in the middle with moderate conductivity and moderate expansion. So pretty much this whole table here, this table helps us choose materials for engineering applications like heat sinks, cookware, or components exposed to temperature changes. All good. Next, we have thermal expansion. So, give me a second here. Most materials expand when heated. The relationship between temperature change and change in length can be expressed by this formula here. We have your final length subtracted by your initial length over initial length is equals to alpha L multiplied by change in temperature. So really, we could write this formula as change in L, delta L, over initial length equals to alpha L, change in temperature. So we got your initial length over here, your final length, change in temperature, and your linear, the alpha L is your linear coefficient of thermal expansion. Heating or cooling affects all the dimensions of a body with a resultant change in volume. Volume changes with temperature may be computed from same formula as we have here, but we have volume instead of the length. We have your final volume subtracted by your initial volume, or your initial volume is equals to alpha V delta T. So this time we got initial volume, your final volume, your change in temperature, but instead of having alpha L, we have alpha V. That would be like the volume coefficient of thermal expansion. And really good note here, for isotropic materials, your volume coefficient of thermal expansion is approximately equal to 3 times the linear coefficient of thermal expansion. Here's a quick little example here. It's pretty straightforward. Let's start off by writing the givens. A steel rod has an initial length of 2 meters at 20 degrees Celsius. If the temperature increases to 80 degrees Celsius, how much does the rod expand? And we have our linear coefficient of thermal expansion here as 12 times 10 to the power of negative 6. Okay, let's write the givens here. We have our initial length is equals to 2 meters. Our initial temperature is 20 degrees Celsius. Our final temperature is 80 degrees Celsius. And our alpha L, which is the coefficient, is 12 times 10 to the power of negative 6 per degree Celsius. And let's calculate the change in T as well. So final minus initial, be 80 degrees minus 20 degrees. So our change in temperature is 60 degrees Celsius. Now we will get the formula that we have in here, and we will solve for the final length. So we have delta L over initial equals alpha 1 delta T. And then solving for delta L, we will get alpha 1 multiplied by delta T multiplied by the initial length. So we got 12 times 10 negative 6 per degree Celsius. Change in T is 60 degrees Celsius. And then our initial length, which was 2 meters. And then solving all of that, we will get 1.44 times 10 to the power of negative 3 meters, or 1.44 millimeters. All good? Let us now move on to thermal conductivity. So, sorry. Thermal conductivity is pretty much describes how well a material transfers heat. Looking at the notes here, thermal conduction is the phenomenon by which heat is transported from high to low temperature regions of a substance. The property that characterizes the ability of a material to transfer heat is the thermal conductivity. It is best described in terms of this expression right here. So thermal conductivity, it would be your Q, heat flux, would be negative K dt over dx. So your Q here would be the heat flux, and the K would be your thermal conductivity, and dt over dx would be the temperature gradient through the conducting medium. Looking here, we have like a pretty straightforward example yet again. A copper wall has a uniform temperature gradient from 120 degrees Celsius on one side to 20 degrees Celsius on the other side. The wall is 0.02 meters thick. If the thermal conductivity of copper is 390, calculate the heat flux Q. So just like any other problems, we will start with the givens. So we have our K is equals to 390. And we also have our change in temperature, which would be 120 degrees Celsius minus 20 degrees Celsius. That would be 100 degrees Celsius. And our delta X would be 0.02 meters. To make things easier, we could actually calculate the temperature gradient first, so we can just like plug that in later. So dt over dx would be 100 divided by 0.02. And again, these units here are what we calculated here, or was given actually, sorry. So that would be 5,000 K per M. And now solving for the Q, remember our formula was negative K and our temperature gradient, dt dx. But we already calculated that, so we are just going to plug values in. I mean, negative, and then our K multiplied by our temperature gradient, which was 5,000. Our Q would be negative 1.95 times 10 to the power of 6 W per meter squared. Pretty straightforward. And the last one that I'll be talking about would be thermal stress. Thermal stresses occur when a material wants to expand or contract due to temperature changes, but something is preventing it or constraining it. The magnitude of the stress resulting from temperature change can be expressed as follows. We have hold on here, give me a second. So we got sigma for stress is equals to E alpha L. Remember we talked about alpha L earlier, and then change in temperature. So really we could write this formula as sigma equals to E alpha L delta T, where E is our material's modulus of elasticity, and just like we talked about earlier, the alpha L is our linear coefficient of thermal expansion, and delta T is the change in temperature. The stress is compressive, meaning it's being compressed, like say for example this one here, like a material, it's being compressed like that, forces, when stress is less than 0 because rod expansion has been constrained. Similarly, if the rod specimen is cooled, tensile stress, not strength, apologize. Tensile stress is imposed when the stress is bigger than 0. And you can imagine it as a force pulling away. And for our last example, we have thermal stress created upon heating. A brass rod is to be used in an application requiring its ends to be held rigid. If the rod is stress-free at room temperature, what is the maximum temperature to which the rod may be heated without exceeding a compressive stress of 172 MPa? Let's not mind this PSI over here because we won't be using that. We will be using MPAs for this problem. And assume a modulus of elasticity of 100 GPa. And again, ignore that PSI over there. So, to start, let us yet again write the givens. So we have our initial temperature, which was 20 degrees Celsius, and then we're trying to find our T max, which is pretty much the same as our T final. And then, that we have our stress is equals to 172 MPa, and then our Young's modulus was given to us, and it was 100 GPa, or in this problem, I'll get to that later actually. Let's just write the givens first, and then our coefficient would be 20 times 10 to the power of negative 6 per degree Celsius. Now let us write the formula. So we got sigma is equals to Young's modulus, coefficient, and our change in temperature. Now we are going to be solving for the final temperature, remember? So we will solve for that. Let's go to it step by step. So what we're going to do is we're going to isolate TF. So we're going to divide both sides by the E and that. So it would be equal to TF initial. And then we're just going to finalize our formula. The final temperature would be equal to stress over E, linear coefficient, plus the initial temperature. That's going to be our formula. So it's pretty straightforward. We're just going to be plugging our values in. our stress would be 172 MPa divided by our E. Our E was given as 100 GPa, but we need to convert that into MPa so that our answer would make sense. It's pretty easy. You just multiply it by 3. So that would be 100 times 10 to the power of 3 MPa multiplied by our coefficient, which was 20 times 10 to the power of -6 per degree Celsius, plus our initial temperature of 20 degrees Celsius. Now, solving that, we will get 86 degrees Celsius plus 20 degrees Celsius, and our final temperature is 106 degrees Celsius. Pretty straightforward, just basic math. And that's pretty much it. To summarize everything, we talked about 4 main things. We talked about heat capacity. Heat capacity represents the quantity of heat required to produce a unit rise in temperature for 1 mole of a substance. It is termed specific heat as well. And the next one, we talked about thermal expansion. Solid materials expand when heated and contract when cooled. The fractional change in length is proportional to the temperature change, the constant of proportionality being the coefficient of thermal expansion. And the third one was thermal conductivity. The transport of thermal energy from high to low temperature regions of a material is termed thermal conduction. And the last one is thermal stresses. Thermal stresses, which are introduced in a body because of temperature changes, may lead to fracture or undesirable plastic deformation. Thank you so much for listening, and have a good day, everyone. Thank you, Dr. Kyle Rogers.